Good morning. Thank you for coming for my talk about the Elvish language. Sorry, I meant metaprogramming. I assure you it's going to be something interesting, something that you can learn from. We will have a lot of code snippets here that actually compiles. It's not PowerPoint where you can actually use those things. We will talk about how we created concepts from templates, how template metaprogramming became better and better from each version of C++ that is used. And hopefully you will enjoy all those tricks, and then you will understand how concepts made everything even better. So let's start. I'm Alex. A few words about myself. I have more than 16 years of experience in C++. I always used metaprogramming since the first day when I started using C++. I love it. I love the pain. Go figure. And I'm working for a great company called Speed.io. We are developing the next big thing in big data. We're developing a new CPU that is not von Neumann, and we will accelerate queries with it. On Monday, I gave a talk about our architecture, so if you're interested, it's already up on the site, and you can go watch it. I have a LinkedIn page where I put posts weekly about C++, things to learn about, sometimes riddles, but even from riddles, you can learn new things. Now, let's start talking about templates. So what is the first thing that comes in mind when people hear the boogeyman word, templates, template metaprogramming? Usually, people go into shock and panic. They don't want to see it. They don't want to hear about it. When I was in other talks that used metaprogramming, all people ask the same question. How the hell do you debug that? What do you do with it? And it's not that hard when you start to understand what it is and how it works. So there's a funny story about it. In my previous job, I have developed an infrastructure that used metaprogramming. When something didn't work, people used to come to me directly because they said, okay, your thing doesn't work. I don't want to look at it. I don't want to understand what's going on. Fix it. And I guess basically it might happen in all places where you work as well if you have a heavily metaprogrammed thing. So because metaprogramming is so hard, we will start stretching out. We will do some stretches, but you have to understand that there's nothing basic about templates and metaprogramming, so even our stretches will be a little bit harsh. Okay, let's start with function template metaprogramming. What can we do with functions and template? Function can be fully specialized, function can be overloaded. Here we have an example of a print function where in lines 6 and 7 you can see the base template that prints anything. And then you have a full specialized function print that prints only ints. In the main, you have print of a string and a print of an integer. And as expected, you will get t1, t-int equals 1. But we cannot do this. We cannot specialize. And frankly, our good friend, the compiler, in this case, tells us exactly what's the problem. As you can see, we're trying to do something for any type that is a pointer. And the compiler tells us you cannot partially specialize a function. So don't do that. Now, what can we do? We can overload. Here we see the same function, the print, the base template. And afterwards, we see a function that is overload of that. And it basically does almost the same thing that we wanted before. We will get everything that is generic t-type, pointer, and we will dereference it and print it in the same way. So here in the main function, we have int I equals 1. We will print the pointer, and we will print 1 itself. And as expected again, we are getting exactly what we wanted. We will get t star 1, t1. Overloading and specializations are tricky. Let's look at a very, very famous example by Herb Stout about print again. So here we have a base template print that prints generic. Afterwards, you have an overload function that prints overload. After that, you have a fully specialized function that accepts only doubles, the pointer to doubles, and it prints specialization. In the main, we're having a double, we're initializing a double, and printing a pointer to that. What will be printed? As expected here, specialization will be taken. But let's look almost at the same example. The only difference here is that we took the specialization and we brought it to lines 35 and 36, and then we are doing the overload. What do you think will happen here? Surprise, overload. Why did it happen? Because overload resolution considers only the base templates. When we did the specialization on the second example, we did the specialization on the first base template. Afterwards, when the overload resolution saw that we have another overload for the same function, it will always think that this function is the most specialized one. And a lot of people get surprised by that. So don't use overloading and specialization. Always use overloading that can do almost everything for you. Now let's go to classes. We will not discuss classes a lot because we need to continue, but you can do with classes everything that you couldn't do with functions. You can do partial specialization, you can do full specialization, you can do base templates. That's what you see here. And then we can initialize all those things in the same way. If they're specialized, if they're overloads, everything works. In C++ 17, we got something really cool that's called deduction guidelines that helps structs and classes to feel more like functions with template deductions, but we will not go into this in this talk. Okay, now we are warmed up a little bit about what templates are and what we can do and cannot do with those. We will start going down to the rabbit hole. We will see trait library for constraints. Trait library was introduced in C++ 11, and it got many useful traits that you can query your type on. For example, here I just wrote a couple of those. We have isPointer, isAbstract. You can say if t can be convertible to you, or is t the same as you. This is very important for the start of concepts. We can constrain our types with those things. So now let's use those constraints and implement it with traits. Let's look at this first example. A very simple function that we already seen before. It's a void print. It takes a const reference to t, and it prints it. Do you see any problem that might happen with this function? Sadly, there is a problem. If you will pass a pointer to that, it will not be able to print it. So what we see here, because I'm using a very cool library called FMT, and I'm using print from FMT, it will actually tell me without shouting too much of the template metaprogramming errors at me, telling me that the static assert failed because I can only print something that is void pointer. I cannot print this. And in this case, it wasn't a void pointer. So how can we fix that? One of many things that we can do to fix what we've done here and detect if we are using a pointer or not is to use the traits that I have showed before. So here we are creating something. We are creating a class that's called print helper. Inside print helper, we have the print function that uses, and the print helper is templated on a type and a Boolean. Afterwards, we have another print helper that is partially specialized on the type, but it always will take the second one if it's true. And we have the function, and now that we know that we have the specialization, this specialization will work only on pointers. Then we need to create the actual function that is templated as well on the type only. It accepts the tconst reference t. It uses the print helper. It initializes it with t and the constraint std is pointer t value, and then uses print from it. By that, you will always get the correct specialization because isPointer t value will say true or false. If it's true, it will go and print the pointer for you, dereference it. If it's false, then we know it's not a pointer, and we'll just print the type as usual. Of course, we forgot about one case that is really spooky. void pointer. We cannot dereference void pointer. I haven't forgot about that. I will just not do that because I wanted a cleaner example. In C++14, traits got some aliasing that tells you what's the inner type of the trait to get it a little bit cleaner to code with it. In C++17, we got value of the traits, aliasing for the values that are inside the traits. Here we can see the implementation of those special aliasing. For example, add pointer t, it's just telling us go into the add pointer trait and take the type. For isPointer value, you're just going into the trait and saying, give me the value. And easier to write, less metaprogramming stuff, less dots, and less things to write. And here we have an example using that. So it's almost the same functionality that was used before, but here you can see that it's cleaner. Instead of saying, I want to take something from isPointer, we're saying, OK, I need the value from isPointer, and then it will do the same thing. Not a great success, but still cleaner. To do it a little bit better, instead of using structs or classes, because those sometimes you will need to write more boilerplate code that you don't actually need, and functions actually do the type deduction, we will want to use a function here. So what we do here, we use something that's called tag dispatch, and we will use isPointer type to our advantage. Basically, the type that is inside isPointer t is std true type or false type, and this will be our dispatch. So in this case, we have a function that is templated that's called print helper, and it will take false type and the t, of course, and then we have another print helper overload that takes true type. For true types, we know it's a pointer, and we need to dereference it. And then we have the template, the print function itself that is templated on t and takes t and uses print helper and takes the type from isPointer, initializes it, sends it into the function with the t. By that, we know exactly what we need to do, so it will be dereferenced or used as a regular type by the tag. Already, it starts to be a little bit more clean. In C++17, we got a cool thing that's called if const expression. If const expression, during compile time, it will look at the Boolean equation here and say, if it's true, I will take one branch. If it's false, I will take the other branch, and the other branch will be removed from your code. So now it's getting very, very clean. It's nicer. C++17 gave us this power over our compile time. In C++20, we can see the first concept that we will see during this talk, auto as a parameter to a function. So here we can say that print gets auto reference t, or the other print that overloads will take pointer to t. It will work, but you can see that something here is not quite the same as it was before. It's not const. It's not const because if it was const, it will be ambiguous. It will be ambiguous if it will take an R value of a pointer. An R value of a pointer in a const reference can be interchangeable. So what can we do? I'm jumping the shark here a little bit, and let's just say I have a concept that's called a pointer. We can write it as we wanted before. So we are saying we have a print function for a regular reference, and then we have a const pointer auto that says this function can take only pointers, const pointers, and then it will work. It's clean, it's expressive, you can understand exactly what we're trying to do here, hopefully, and that will work, unlike the other one. Okay, let's get to the main event. We are trying to write a concept or a trait that detects a container. So to detect a container, there are few ways to do it, but let's start with a naive way. A naive way will be saying that every container in the standard has a nested type called iterator in it. We can use it to our advantage. So basically, we need to create some kind of a struct that will do some kind of templated magic and will give us a value if it's a container or not. Seems easy. To do that, we will need to understand a couple of things before we can implement it. So sFine is one of the most important things in a language before C++20. It's a special rule for templates overload that says if one of your templates actually has an error, but it has an overload that works, do it quietly. Remove the error and just use the correct overload. How we will use it to our advantage? Here we need to understand another thing. In the overload of functions, when we're using ellipses, those 3 dots, there will be always inferior function to a specific function. So here we have a cute example of that. We have a print function that takes ellipses, and it will print ellipses out. And we have a function that takes an integer in, and will print integer. In the main section of the code, we have print 17, and print 17 is a string. As expected, you will get integer in the one that uses integer, and not the first function with ellipses. And then you will get ellipses, as expected again. Note that ellipsis is any number of types or any type, but still the overload decided to take the more specific overload for this. Now we can actually use it and implement our naive way of detecting a container. So what we need to do? We need to create a templated type that's called isContainer that is templated on T. Then we have a function inside that struct that is F. We don't care about the name. It receives ellipses, and it will return a byte. Has no body. We don't need a body for that. And it's templated on another template type S. Then we have an overload for that function that is templated on S, but it will return size T. And this function will be called if and only if S, the templated type, has an iterator pointer inside it. Now there's a little bit of metaprogramming magic that we are saying we have a static const bool value, and we're saying, okay, if we will invoke this function f with the type t that the class is templated on, and we will pass 0 to it, what will it return? If it will return size t, yes, this is a container. If it will return a byte or something else that is not size t, then it's not a container. 0 can be null pointer, so it works for ellipses because it can take anything, or a pointer. Pretty simple, but hard to understand. How should we use it? Maybe like this? No, we cannot use it because this will only work with C++17, and we don't have that yet. We will gradually continue and understand better what we have in the language and what we had to do before we had all those tools. So what can we do? Like my friend here, Rick, would say, what you gonna do? So we already saw, we can do delegation to a helper class. We can delegate to a helper method. We can do, in some cases, we will just want the compiler to pick the correct function for us, and that we will do with sFine. We already saw that as well. For that, we will need some more tools on our tool chain, on our tool belt for metaprogramming. And one of the most important tools that were introduced in C++11 is EnableIf. EnableIf is an sFine. It makes the compiler to pick the correct function that you want to work with. Here I just show an implementation of sFine, of EnableIf, how it is implemented. Basically, it's something that is templated on a Boolean, and then you have a class that always a void. By default, it's a void. Then you have a specialization for that with true and t. Seems familiar, right? I already showed you something that looks like that. But the difference here is that EnableIf with a regular Boolean that is not true, that is false, it will not have the type inside it. And so EnableIf will be well formed only if the Boolean expression is true. And then we have the aliasing that I already showed before. We have that since C++14. Now, how can we use that for our advantage? We can basically do what we wanted before with two functions. We have one function that uses print, that's called print, that is templated on T, of course, and it received the const reference to T. And then we have another parameter, a default parameter, that is EnableIf T, that says, if this type is a container, then this function will be taken. And then just use the default null PTR into it, because we are saying this is a void pointer. We don't care what it is. We have the second function that's print as well, that uses almost the same thing, but here we're saying, okay, if this is a container, do the same thing. Say that we have a void pointer there, process a null into it, but here we know it's a container, then we must print all the values from the container. And for example, I have the print with 18, which is a regular type and not a container, and I have the print with std array that takes 1 to 3, and it will print 18 and 1 to 3 as expected. Now we can go back to C++17, and again, I just wanted to show you that this example, how cleaner it is and clearer it is without all those things. We can have one function that uses if const expert that says, if this is not a container, please just print a number. If it is a container, print container and print all numbers. Here we have, again, for our example, we have print 2, and then print an array of 1, 2, 3. And as expected, we have 2 and container 1, 2, 3. To progress and create a better concept for detecting the container, we need more tools. So another important progress from C++11 was variadic templates. Variadic templates means that you can create classes or functions that can receive numerous different type into a function or a class. Here I just wanted to show you a small example from C++17 for a trait that's called RAllIntegral. RAllIntegral is inheriting from std conjunction. Std conjunction is a really great tool to say, if I have more than one expression, more than one templated expression, I will do AND between each and every one of those. So in this case, we say, if T is an integral, please check it for the whole pack. Unpack it, do an AND between them, and give me an answer, true or false. std conjunction do it for you, so you don't have to write the T thing or anything else. You just use it as is. You're passing the types to it. You're passing the class. And here is a usage example. Again, we have a template, a variadic template of many types. We have a function that's called check that's saying I will use all those variadic packages. And inside the function, we're using a static assert that says RAllIntegral, please unpack it and give me the value from it. And because we inherited from conjunction, we have value and type inside it. Now, another important tool is void_t. Void_t is basically a neater and a nicer way to say, I will be a well-formed void if and only if all types that you use to declare me will be well-formed. And then we will have a type. Very similar to EnableIf, but cleaner. That's how it's implemented. Very simple. It's just a template that takes a variadic number of arguments inside it, types inside it, and saying using void_t equals void. So it will be void only if everything inside those brackets will be well-formed. And thankfully to Walter E. Brown, we have that in C++17, so use it. It's much cleaner than EnableIf. Now we're getting to concept. Now that we have all this tool on our belt, we can actually create a very interesting concept, unlike before that was very naive. So we already saw some concepts. We already saw a naive container. It was a concept. We saw all-integral. It is a concept. Auto-function parameter. It's also a concept. Now we will create our special, heavy concept for detecting a container. And it is heavy. Each container type in C++ standard needs to be contained with all those 6 functions, all those 6 constraints. So basically we're saying, if this type is a container, we can use std_begin on it, and it returns the begin iterator. We can use std_end on it, and it will return the end iterator. We can use begin and end iterator should be checked with not equal, and the result should be a Boolean. Begin iterator has a ++ function operation. Begin iter has a dereference, which returns something that is not void. Begin and tail iterator are copy constructible and destructible. So if we will see that the type has all these constraints, we can be certain that this is a container. With our previous implementation, we cannot be certain. Let's start implementing it. For the implementation, we will need a lot of helper things, a lot of helper types. So for beginning, we have something that's called tBegin. It just says, okay, please see if this thing can be used inside std_begin and give me the type that is returned. Here I'm using something that's called decalval. Decalval was introduced in C++11. And it says, I want to initialize this type, but I don't know if it has a default constructor. So decalval will construct anything for us. Even if it doesn't have a default constructor, it will do it. It is good only for compiling, during compilation to check restraints if things are working. It will not create a full object because it can't, but it's very useful to see if this type of object can be used inside a function or something like that. So that was our tBegin. Then we have tEnd. tEnd is very similar, but tEnd asks about std_end. Can we use this type on std_end? Afterwards, we need to see if those types are not equable. So we are passing begin iterator type and an end iterator type. We are saying we are creating bi with decalval. We are creating ei with decalval again. We are trying to use the not equal operator on both of those, and we are taking the type that was returned, and this will be our type. Then we need to create tincable. That means that it can be increased. So again, you should be very familiar with it by now. We are using decalval to create the type, and then we are using ++ on it, and we are saying, okay, give me the answer from that. Then we are creating a tderefable. So again, we are using the same thing. We are using decalval on the begin iterator, and we are dereferencing it and taking the type with the decalval. All that was just a preparation for our container. Until now, we did nothing. This is the first step, and the easiest step that you will see for this, creating the base template type. So we have a template that takes C, some type, and we have a type named void, just something that can be passed in. It will always be void. In this case, we are saying, okay, it's a new struct that's called isContainer, and it inherits from std_false type. It's easier to inherit from std_false type because std_false type will always contain a value inside it that is false, and it will have a type that is a Boolean. And this is the magnificent thing that you need to write to create this horrible, horrible concept for it. So here you can see that we are using a struct that is a partially specialized from this previous struct. And it's take a C template into it, and then we are using a void T. As I mentioned, void T will be well-formed if and only if everything that is written inside this template is well-formed. So we are saying tBegin should be well-formed, tEnd should be well-formed, increasable well-formed, not equal well-formed, derefable should be well-formed. Then we are using something that is integral constant that was introduced in C++11 as well that says this will be a constant of type bool, and the value will be whatever is created down here. So we are saying if those things are convertible to bool, if the result of the T not equal are convertible to bool, use them. If it's destructible, and if it's destructible, and if it's copy constructible, and if it's destructible for and if it's copy constructible for only then pass a void into it. And then it will be this will inherit from the proper type, because we're inheriting from std integral. How to use it? Here are some examples of usages. So we have a template function that is a const expert function that says, is it a container? It receives the C type that we are passing to it, a const reference to it. Then it just returns is container C value. Easy as that. Afterwards, we have another example of two functions, get first one and get first two, where get first one is just getting the first value from the container. And the only difference between those functions is that the first function uses EnableIf on the return value. We are saying here that enable this function only if the C that you are templated on is a container, and the type name that will return is a C value type. Value type is something that is contained in all of the containers in the standard, and this is the type of the value that is contained in them. The other example uses EnableIf inside the template. So here we are saying, okay, we want something to be templated on C, but this C must be a container. If it's not a container, this will not work, and this will just print out a very, very nasty thing on the screen. So problems. There are a lot of problems with this approach. First and most, it's really hard. It was really hard to develop a new concept until C++20. The error messages are horrible when you use those things. So when you will need to debug it, you will cry, you will beg, you will pray, you will go to all grief stages, and then you will end up with something that works, maybe. EnableIf and void t, even if void t is a little bit more readable, most of people cannot read those things. They don't understand what's going on, and it's not maintainable. So this is the Elvish I was talking about at the beginning of the talk. We cannot read this, we cannot use this. But there's an answer to that. C++20 concepts. In C++20, concepts were introduced, and concepts made our metaprogrammed code cleaner. We can use it easily, we can produce things in an easier way, and I will show you a couple of examples. So with C++20, it's really easy to create a concept. Let's start with a concept that we will use later, but this form of this concept is a little bit more complex than what we actually need. We will see it later. So here I want to see if types BI and EI, begin iterator and end iterator, are not, operation not equal, can be performed on those types. You're starting with a template as usual, then you need to write concept, and then you need to give it a name. Afterwards, you need to write a require expression. You need to write a require expression. So the require expression is interesting because here you are getting BI and EI as actual objects. You don't need to use decalval anymore. It is done for you. You are getting those types even if they are not actually created. You can see if they're constrained on something without doing it. It's cleaner. It's understandable. You can understand what is written here. So we are saying here inside the requires expression, we are saying if BI and EI are not equal, can perform not equality on them, and the trailing return thing says that if the return of this operation is convertible to bool, then the requires are met. Understandable, readable. The usage of that is simple as well. We're starting with a template function that receives the BI type, and then we're saying the second type that we want to use, it's not just a type name. We want to constrain it. We want to say it has to be not equable with BI, and we say that type will be called EI. Another good thing about concepts that the first parameter to a concept will be taken automatically. So as you can see here, I don't need to pass BI and EI together. I just need to pass BI to the concept, and EI will be consumed automatically. And the function is simple. We are just saying, okay, if this will be met, then we just can return true. Simple function. Here's an example of a usage. So int and long, they can do the operation, and therefore, it will be okay to use it. Here we have an example of an error. Now we are trying to see if int is not equal to an iterator inside a vector of ints. They are not. But look at the error that we are getting now. It's understandable again. So the compilers tell us this function foo cannot run. Why it cannot run? Because the concept is evaluated to false. Then you can say, why it's evaluated to false? It will tell you, because BI not equal EI would be invalid. Understood. You can now go and fix it. All requires or all concepts can constrain in different ways. So we have a couple of ways to do the constraints. The previous way that I show you is inside the template itself, but you can do it like that as well. Here we are saying we have a function that is templated on BI and EI. We are saying here in this type of thing that we require those templates to be not equable. So here I have to pass BI and EI to them because it's not inside the template declaration itself. And we are saying this function receives BI and EI. The requirement says that it can be not equable, and we will return true. Another way to do it is to make the require clause on the function itself. So here we are saying this is a templated function that uses BI and EI. It's a const expression. It receives BI and EI. And those BI and EI should be not equable. Again, simple. Each and every one of those usages is good for a case. Sometimes it's for classes, sometimes it's for functions, but we always have a case for that. Another thing that I already showed you in one of my previous or first slides is constraining an auto. So here we can see it again. We can say, okay, the first type can be any generic type. We don't care what type it is. But the second type, it's auto as well. But we want it to be not equable with the type of BI. And we have to use decal type here. And then we're saying auto AI. So the auto will be constrained only on types that are not equable with BI. Okay. Now let's implement our is container, but with a new concept, not with traits like we implemented before. It will be easier, it will be cleaner. So let's start with not equal begin and end. Here we say that this concept is templated on C. C will be a container type, and we are saying this concept requires that we will get a C that can be used with begin, end, and can be used with the operator not equable. And their result should be the same as bool. So we are looking just for something that is a Boolean. Afterwards, we need to create another concept that's called beginable. Very similar, you will receive the require clause here, require expression here that needs to get an object of C, and this object should be usable inside std begin. Same thing for the endable, just with std end. Let's continue. Begin should, the return from begin should be incrementable. So here again, we have a concept that receives a C. This C should be used inside the begin, should be usable with begin, and then should be incrementable. Simple, expressive, you say exactly what you want to do here. Afterwards, we need begin derefable. Very similar, just instead of plus plus, we're using deref. Then we need to see if something is something that is returnable, derefable from begin, is not void. Here we need to do a little bit, it in a little bit more tricky way, because here we are saying, okay, will something return a void? So I'm saying here, if C can be used with begin, and then if it's derived, will it return a void? Afterwards, we can create a concept that is a little bit bigger. So we need to check if We need to check if its begin and end are copy, constructible, and indestructible. We can do it in one concept. We say, again, it's templated on C. It requires us to receive this object of C type. And then we need to see, we actually use concept from the concept library here that are saying, are those things destructible? Are those things copy constructible? And this is the concept itself. The concept just uses requires clause. It says this concept will be constrained and will be okay if and only if the type that we are templating on is beginnable, endable, begin incrementable, begin dereffable, not equal begin and end, not equal if the begin is dereffable and not equal to void, and begin and end copy constructible and destructible. As you can see, it's smaller, it's understandable, it's readable, it's debuggable, and the most important thing, you can do it even sleeker and smaller than this. I just wanted to show you the process of how it was created with traits, and here I'm doing the same thing, but basically, I could remove the beginnable and all other stuff because I'm using std begin and std end almost in each and every one of those concepts. Okay, usage examples. So what can we do with this thing? We can use it in static assert as we used it before. So we're saying here, is this thing a container? Is a vector of ints a container? Yes, it is. Then we can use it inside the function. We can say, okay, I want to see if first elements of two containers are the same. So here we see a function that calls is first item the same. We have container out to C1 and container out to C2. We're constraining autos again to receive only things that are containers. And then we are saying, if we already know that those things are containers, we can use begin on them, and we can deref the begin, and it will not be void, and that's it. You don't need to ask any other question. Here, for example, I have a vector of integers and an array of integers where the first element is actually the same. So if I will return is first element the same, it will return true. Don't mind that I'm converting a Boolean to an integer. Another example for an error this time. So the same function that we defined before that constrains only on containers, now we want to use it on a vector and on a tuple. Tuple is not a container, so what will we get here? Again, a pretty much readable thing that says is first cannot be run because something will fail, and in the end of this error you will see exactly what constraint was not satisfied. It's saying std begin cannot be performed on a tuple. Please go change that. The error is manageable, is readable. Again, I'm just stating that because when you're working with metaprogramming for a long time, the errors that you get are 2 pages long and they're horrible. And here you get something that is really small and points you to the direction that you need to fix. It's something that we didn't have beforehand. In conclusion, concepts simplify the code. They do. They make everything smaller, smarter, cleaner, maintainable, understandable. We're doing interesting stuff with them without sfine, without EnableIf, without the grief of reading template errors. It makes metaprogramming easier. So now users that don't know how to write templates can read it, can understand what's going on inside it. It makes the code better. It makes other users to want to actually use it. In my opinion, it's really great. And here is just to finish up, we can see what the first one, what the concept that we created in C++17, how it looked like. And this is just the first part, the last part. We had many more things that we had to create beforehand. And here we can see the concept. Smaller, you can actually read it. You understand it, it's expressive. We want all those things to be true, only then it will be constrained to be a container. It's wonderful to use something like that inside your code and not to be constrained to those horrible templates. And as the robot says here in the end, it's 83.6% readable. We have more time to go here. It will be more readable. I think with each version of C++, we're getting cleaner and cleaner with our metaprogramming. And I was approached to the stage before I started by Daniela, and she told me, I would like this to stop to call it metaprogramming. It's not metaprogramming, it's just programming. And it is, it's becoming the thing. It's not metaprogramming anymore. It's understandable. We don't need the tricks. We don't need SFINE. We don't need EnableIf. We don't need those things. It's just overloading a function as any regular function you would overload. With this power comes better programming if you use it correctly. So thank you very much for listening. Anyone has questions?
We have one question online from Brandon. Can you create a concept that enforces things about a type alias? For example, I want a concept that enforces that t::: value type is integral.
Yes. It's just using a concept. So inside the require clause, or even you can do it with an expression or a clause. You can just use a concept that's already inside the library that says exactly that. Is integral, I think. And if not, it's really easy to implement your own concept with a trait. So you're saying this concept is integral or integrable or whatever with std is integral, and that's it. Daisy.
Inside the requires to make that happen, but yeah. Anyway, I have two questions, or two gripes that I'm going to phrase in the form of questions because that's a terrible thing to do, and I'm going to do it anyway. First, thank you for pointing out that this is not metaprogramming, but I disagree with your reasoning. Metaprogramming can be completely readable, but this is not metaprogramming, it's generic programming. I didn't see anything in here that was what I would call metaprogramming. These are all generics. These are ways of describing types.
Yes.
They're not ways of generating, running algorithms at compile time, in my mind. Second gripe that I'd like to hear your comments on. You say you like void t better than EnableIf. Have you looked at error messages when you use, in a very recent compiler, when you use EnableIf instead of void t? And what has been your experience? And then also in terms of expressiveness, do you think that void t is more readable than EnableIf in terms of a name?
In terms of a name, no, absolutely not. In terms of readability, it uses less code and it's more understandable if you understand what it is. As always with C++, you need to understand what you're doing. So in my opinion, if your code gets cleaner because you use something that is more correct for this, or it's smaller and more compact, then it's better. That's my opinion. And what was the first part, I'm sorry?
Have you checked with a relatively recent compiler what error messages EnableIf gives, and do you recognize them from concept error messages?
Yes, they're very similar now. Yes. Yes.
Hello, thank you first for your talk. Currently, this is mainly for generic programming, and generic programming cries for libraries. And you, as library author, do not always have control of what C++ standard the user of your library actually wants to use. Is there any advice how I can leverage concepts for the users who have C++20, but still make my library compile on older versions?
If you want to use, as Daisy stated, basically the newer compilers can give you easier way to debug your generic programming. So right now, even if you use EnableIf or void t, you will get those messages. That's exactly what she pointed out. It got cleaner even with those older things. So if your user has concepts and he wants to use concepts with your library, it's easy for him. You can still write it in C++ 17 or 14 or whatever, and the newer compilers will do the job for you.
Okay, thank you.
Yes.
Hello, thank you for the talk. I have two questions. In terms of performance, what is the size of the generated assembly code or the compilation time for using concepts versus EnableIf?
I'm not sure about the generated code. I haven't checked that. I will do that afterwards. But the compilation time is a little bit worse. The compilation times got longer with the usage of concepts. But it's worth it.
Okay, because my assumption is underneath concepts will still need to use declval in order to generate those.
It's inside the language. So declval is something from the standard library. When you use requires, it's from the language. So it's done for you by the compiler. You don't need to use declval.
Okay, okay. And my second question is, when we have a concept variable like a container in this example, do we have something like the lifetime of that variable name or the value category of that variable name? Or if I do a decl type on the concept variable name, will I get a valid output? Is that of interest to
You mean inside the require clause?
Yeah, no, what I mean is you have concept container equal to something, something. Now,
Okay.
does that container name have a lifetime or a scope? Or
No, it's a type. It's a constraint type. It's not a usual type. It's not something that you can instantiate. You cannot create an object from it. It's just used for generics. It's just used to constrain you. So, for example, we had the auto there. You're saying, I want this to be generic, but I don't want this to be too generic, so it can be everything. So concept is just saying there, okay, these things should be constrained only to something that is a container, but it's not a type.
Okay, thank you.
We have another online question.
Yes.
Can we say that concepts completely eliminate svne, EnableIf, and void usages?
Of course not. We still have to be backward compatible, and there are still users that don't use C++20. So you still need to understand all those concepts I have shown during this talk, and you still will need to use it. Hopefully, when time will pass and users will not use something that is not C++20 anymore, and all of us will use concepts, then we will be able to eliminate it. But I think the people from the committee can answer that better. I'm not. Anyone else? Thank you very much.